This is the section on fire protection and bleed air pneumatic systems. First, fire protection. What are the basic characteristics of fire detecting systems that are found on aircraft? Fire protection systems are essentially made up of systems that detect, and then hopefully you have a system that will extinguish. But first, the detecting. If you have a smoke in the cockpit, a fire in the cockpit, you don't need a remote sensing system. But the bigger and bigger aircraft you fly, the farther and farther away you are from the engine, and the more likely you're going to need a sensing system. On a 172, you can probably tell if there's an engine fire, but when you start putting the airplane engines out on the wing or out on the tail, it's going to be far enough away, so just looking in to see if there's a fire is not going to be enough. Generally speaking, when you have a fire detecting system, there's going to be some type of an electrical test you do prior to takeoff. Here's an example of one system that you can move the handle down, the switch down or switch up, and the light will come on telling you that it works pretty good. Wow, 3 systems, probably on a 3-engine airplane. My guess, 727. You're also going to have warning lights, maybe some bells or horns coming on to tell you that there's a fire. We'll get into a little more detail before this section is over. And typically for engines or APUs, the sensing system is either going to use some kind of a system that detects high temperatures or that detects flames. Typically, smoke detection is limited to inside of the cabin or the cargo area or the lavatory, because sometimes engines get a little oil on the outside of the engine and they emit smoke, and it's okay if it's just a little tiny bit, but that would set off a smoke detector. So you don't typically see smoke detectors inside of engine or APU compartments. We're only going to talk about 3 different locations for fire detection systems in AS311 turbine engines: in the engine compartment, in the APU compartment, or the bleed air ducts. And remember, the bleed air duct temperatures are not talking about the temperature inside of the duct. We already know that that air is hot, but if it starts leaking and it's going to heat things up on the outside of the duct, that's when we need to know. So this one might argue that this isn't a fire detection system, but it's definitely an overheat detection system in case there's hot gases leaving the bleed air ducts. Oops. Okay, temperature detection systems. There's typically 2 kinds. Systems that are set up with individual detectors that it'll detect over temperature in one spot. There's a couple of kinds. You don't have to write them down. This one uses 2 different pieces of metal, and when they get hot, they change size, they expand. One of them is a different kind of metal than the other one, and these 2 contacts touch, and that's essentially a switch, turns on a light. Another kind is a thermocouple. You don't have to draw this on the test. A thermocouple symbols like this, and this piece of metal right here and this piece of metal are different, and where they touch, when you heat it up, it gives off electrons and causes current flow, and you can use that system to turn on a warning light or a bell in the cockpit when this starts generating a millivoltage. A thermocouple, this is the same theory of operation as an EGT probe. 2 different metals together, when you heat them up, produce a very, very small voltage or a very, very small amperage. You can use this for a heat detection system. And here's a classic system. Any one of these temperature sensing probes distributed throughout the engine compartment. Any one of them gets too hot, closes a connection, and you can have a light come on or a bell come on. And here's a test switch. You close this switch right here, and it'll make the bell come on even though there's no fire, so you can at least see if the system is working. Another type of temperature system is measuring temperature or in an area. For instance, if you have an engine compartment, and here's our engine. And there's going to be some space in here between the engine and the metal. There's going to be some space in here. And so you can run your temperature probes inside of there to tell you whether or not the engine, outside of the engine, if there's fire coming out of the engine. A really typical way is to have a very small tube. It's less than 1/8 of an inch in diameter. There's more than one kind. Essentially, the material on the inside changes electrical conductivity when it gets hot and allows current to flow from the outside case through the material and then into the center wire, and that turns on a switch. And so this one loop can be really, really long and run all through the engine compartment. And anywhere that it gets hot, or if the whole thing gets hot, then it'll cause the system to actuate and tell you that there's a fire. Here's a picture of what it looks like. And it's typically mounted inside of on the wall of the engine cowling. And this is a loop type system. There are flame detectors. I don't have a good picture of one, and it detects infrared light. Infrared light is invisible, but it does carry a lot of heat energy. If you've ever stood next to a fire, even though you were upwind and the wind wasn't blowing the heat towards you, the infrared light, the infrared energy coming off of the flame can hit you and cause you to warm up. So there are some fire detection systems that detect infrared light to tell you, the pilot, that there's a fire somewhere. Okay, that was fire detecting. Now fire extinguishing. You got to have heat and fuel and oxygen to get a fire. Usually the heat is going to be coming from the engine. The fuel could be the jet fuel, and of course the oxygen is coming from either inside of the engine or on the outside of the engine. There's only 2 extinguishing agents you're likely to see in an engine compartment. CO2 is pretty old school. You're going to only find it in much, much older airplanes, like several decades ago, like pre-1960, because then they started coming out with the halogenated hydrocarbons, or the industry standard term is halon. Here, halon. Oh, halogenated hydrocarbons. There's several different kinds. When they make new ones, they give it a different number. I'm sure they've gotten into the 1400s by now. The higher the number, the better extinguishing job that it does, the less toxic it is to human beings, and the less crud is left over after the fire is done. So when I was flying on B-52s, we had 1101 in the cockpit in our handheld fire extinguishers, and if you used it because it was reasonably toxic, you had to put on your oxygen masks to 100% oxygen so you wouldn't breathe anything in, and then there was crud left over after you were done. But you get into the 1300s or higher, and it's pretty much not toxic, doesn't leave anything left over, and it extinguishes fire better than any other kind. Here's an example of DC-10. There's a couple of fire bottles, a couple of extinguisher containers. Either one can be blown and allowed to go up to the engine compartment and spray halon into the engine compartment. Here is a picture from the bottom of a fire bottle, and here are the wires coming in, and that's going to fire an explosive device, a very small one called a squib, and make it blow. An HRD system. HRD stands for 4 words. High rate of discharge. It's called high rate of discharge because when you fire this extinguisher bottle, it discharges really, really fast, only a second or 2. I've only seen halon or carbon dioxide in either of these systems. And the vernacular in aviation is to call this the fire bottle. They really probably ought to call it the anti-fire bottle, but I guess you use it in case of a fire. Besides, nobody asked me what I thought it ought to be. Here's another picture of a fire bottle. They're at high pressure. They're usually spherical, and there's usually a pressure gauge on them. The explosive squib. Here's a diagram of a typical fire bottle. There's going to be a wire coming up to this explosive device, and it's just gunpowder. But if the electrical contact is made in the cockpit, if you pull the handle and push the button for it to fire the fire bottle, it's going to blow, and break this frangible disc. Frangible means it breaks. So this disc is going to break, and all of the gases are going to leave. This right here is essentially a screen to catch the frangible disc parts, but all the gases get to leave in 1 or 2 seconds and go right into the engine compartment. And of course, there's a gauge so you can pre-flight it and see if there's enough juice in it, enough pressure in it. Quantity, just like I said, PSI is how you're going to tell if a fire bottle still has the extinguishing agent in it. Of course, gases tend to change pressure with temperature. Here's a temperature correction chart. This one is in degrees Fahrenheit. It says at minus 40, the minimums and the maximums ought to be between 60 and 145 degrees psi, but on the other end of the scale, if it's 100 degrees Fahrenheit, then if it's a fully charged bottle, it ought to read somewhere between 438 and 523. So you're going to have to estimate what's the temperature of the gases inside the bottle, and then look at this temperature correction chart to let you know whether or not the fire bottle is actually full. Now, commonly with HRD systems, you're going to have a red disc and a yellow disc on the side of the fuselage or somewhere that the pilot can look at, or the ground maintenance personnel, whoever's doing the pre-flight, can look at to see if the bottle has blown. For instance, it's typical if the pressure in here gets too high, the forces may be exerted on the bottle, and they make this bottle, just barely strong enough so it could blow the bottle. So literally what they do is they have a fusible plug right here, and this thing melts with temperature. It's extremely similar. In fact, it's the same concept for a fusible plug on an airplane wheel that melts in case it gets too hot to prevent the tire from overpressurizing. If this whole thing is getting too hot, then the pressure in here is going to go up. At some point, the temperature will get hot enough that this metal will melt and allow the gases to leave. Well, there's going to be a tube coming out to the side of the fuselage, and right at this tube, there's going to be a red disc. So if you're looking at it from the outside of the airplane and this red disc has blown out, that's telling you that this fusible plug has melted and that the extinguishing agent is gone. Now, you also may see the exact same system with a yellow disc. If the yellow disc is blown out, it means the system got operated. This tube going to the engine, it's just going to have a really, 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 really small line going to the side of the fuselage. And on it is going to be a yellow disc. This yellow disc, if this is blown, that is, if the electrical contact is made in the cockpit, you fire the squib, it blows the frangible disc apart, the gases leave the bottle, the frangible disc parts are held by the screen, and the gases go to the engine. A very, very, very small percentage of these gases is going to blow this yellow disc out. So if you look on the side of the airplane or wherever it is and you see that yellow disc blown, that means, it doesn't necessarily mean a fire, but it definitely means that this extinguishing system has been operated. Here, I wish I knew where I found this. This is off of an APU fire detecting and extinguishing system. Here's the gauge in PSI. I can see a needle point right here. And here's our red disc. If that's blown out, it means the temperature got too high. And to keep the bottle from overpressurizing and coming apart, the fusible plug melted and would blow this out. And of course, if the yellow one got blown out, that means that somebody activated the system and blew the bottle. Okay. APUs, pretty simple. Main engine, a little more complicated. If you have a fire extinguishing system for a transport category jet, big biz jet, big turboprop, even on some smaller aircraft, there's typically some kind of a handle. That handle is going to turn red. There's going to be a light on it, and that's going to turn red. For instance, here is the fire handle, T-handle panel that's been taken out of a 727. If engine number 2 has a fire, then this light is going to illuminate. This light is going to be bright, and that makes it nice and easy for the pilot, because now you're going to pull this T-handle out. You know exactly which one has the fire, so you pull the one that is illuminated. Here's another picture, a diagram of one for 727. So you pull the handle. Well, pulling this handle typically does a bunch of things. First of all, it turns off a fuel valve so the fuel cannot get into the engine compartment anymore. It also typically turns an isolation valve to the off position, so hydraulic fluid cannot get into or out of the engine compartment to or from the hydraulic pump. Although transport category jets, big biz jets, big turboprops typically have hydraulic fluid that doesn't burn easily, if there is an ignition source, it will burn. So you want to try to keep from putting anything more into the engine compartment that'll burn. So if you put the fire out, it can't start up again because there's something to burn. Of course, you might have a fire inside of the engine compartment because of electrical issues, or it might be causing a spark. So if you pull this T-handle, typically, now every airplane's different, typically it'll turn off the electrical power going to or from the engine compartment, or at least from the electrical generator going out to the rest of the airplane. You won't get to use that generator anymore, but that's a lot better than having the engine burn off of the airplane. And of course, you could have fire going through the bleed air ducts, although that's pretty slim. But part of why the engine compartment is overheating is because the bleed air ducts inside of the engine are leaking. And so when you pull that handle, if you've got an engine down here on the pylon coming up to the wing, all of these valves are going to be located somewhere in the pylon so that fuel can't go in, hydraulic fluid can't go in, electrical energy can't come out, bleed air can't go, or I guess bleed air would be trying to go out. So you're essentially cutting off the engine compartment from anything that could either cause more fire to burn or cause more fire because of a source of ignition. Now also, pulling the handle arms the squib on one of the fire bottles, so now when you push the button, excuse me, now when you push the button, the fire bottle will blow and be discharged into the engine compartment. So you essentially have to do two things. You have to pull the handle to arm the squib, and then you're going to have to push a second button. Here's a big transport category jet. The fire bottle is somewhere around here, and the extinguishing agent gets directed into the engine compartment. And that 1 or 2 seconds, it literally floods the whole engine compartment with the fire extinguishing agent displacing the oxygen. And so that's why the fire will go out. Now the good thing is you're going to want to pull that T-handle out, and you may want to wait a few seconds. So if there's any fuel or oil in here that's burning, it'll have a chance to burn maybe some of it out, so that when you turn on the extinguishing agent, there's not any, and it puts the fire out, there's no puddle of fuel in the bottom of the engine that could catch on fire again, hopefully. Bleed air pneumatic systems. What is the purpose of having pneumatic systems on board an airplane? Well, they're there to transfer power. If you fire up the APU and it compresses air and pumps it into the pneumatic system, you can use it to start the engines. You can use it to run the air conditioning system on the ground. You can use this pneumatic power because it's hot, compressed air. You can use it to anti-ice the wings. There's a lot of things you can do with pneumatic power. This power is in the form of installed, or instilled, I guess rather, in air, so it weighs less than hydraulic power systems do, because the fluid inside of it is air instead of hydraulic power. So the overall system can deliver lots of power, but it doesn't weigh as much as a hydraulic system. The disadvantage is that it doesn't have a lot of force. You can't move big things with it. You can maybe move some thrust reversers, but if you want to put landing gear up and down, and if you want to use enough force to move hydraulic powered, or if you want to use enough force to run flight controls, you're going to have to use a hydraulic system. Okay, mostly we're going to talk about the engine uses of the bleed air system and the pneumatic system, and stay away from most of the airframe uses. Of course, if it's a transport category jet, a big biz jet, a big turboprop, or a big turbine-powered helicopter, you're going to use it for engine starting, so that makes it really nice to have an APU on those airplanes. Of course, we've already talked about in the past that you can have a turbine engine, and if you want to cool the turbine case, you can run tubing around the turbine case and bring some bleed air and run through the turbine case, because the bleed air here might only be 200 to 400 degrees, so I'll just say 200 to 300 degrees Celsius, whereas the airflow going across the turbines could easily be 1,000 degrees Celsius or more. So it'll actually contract the turbine case and make sure that there's no space between the, or very little space between the turbine blades and the turbine case. Oh, I guess that's the next one. There we go. I guess I was talking about turbine case cooling. Turbine blade cooling, you can take this nice, reasonably, relatively speaking, cool air and blow it into the turbine blades, the stationary ones, and blow it onto the rotating ones, so the turbine blades can withstand higher temperatures right inside of the turbine section. Of course, back in the oil system chapter, we've talked about labyrinth oil seals. If you've got an engine shaft and you've got a bearing chamber and you've got bearings inside of it and you're bringing in and squirting oil on it, the oil's going to try to leak out. However, if you take bleed air and pump this outside chamber full of bleed air, it'll push the oil back in. And of course, we'll need to pull the oil out with a scavenge pump. But this is going to be bleed air off of the engine compressor that keeps the oil inside of the bearing chamber. Of course, oil engine reservoirs are typically pressurized. We're going to have a little bleed air on top of the oil coming from that oil reservoir, that bearing chamber. Some of that bleed air is going to be routed into the top of the oil reservoir and keep our oil tank reservoir pressurized. Also, we've had a chapter on engine anti-icing, and you can use bleed air to pump to the front of the engine and keep the engine intake warm, or pump it into the bullet so it doesn't have ice sticking to it. And there are some engines where the thrust reverser doors in the back, or if you move the entire cowling aft, if you've got a high bypass turbofan, you may actually move this part of the cowling back and have a door pop up so the reverse air goes forward, and this door may move this actuator. Instead of being a hydraulic actuator, it may be a pneumatic actuator, and it gets its power off of the engine compressor. You can get pneumatic power essentially from three places: from one of the main engines, from the auxiliary power unit on the aircraft, or from a ground power unit. There is, when you're reading pilot operating handbooks or flight manuals, you may come across a couple of these different terms. Bleed air is used for engine purposes, like most of the things on the other slide. Customer bleed air is talking about the airframe customer. Oops. And so the airframe customer is going to need it for air conditioning and pressurization, for anti-ice for the wings, and maybe for some other stuff. So if you're reading and it says customer bleed, it's talking about the engine customer. The engine company is selling it to the airframe manufacturer. So that's the bleed air that's coming off of the engine that's leaving the engine compartment. And just bleed air is being used for the engine itself, like engine anti-ice or to cool the turbine blades. Pneumatic systems on airplanes typically have a couple of indicators. First one is supply pressure. The pressure is usually somewhere between 40 and 60 psi in the ducting in transport category jets and all the other aircraft that have pneumatic systems. And here is a picture off of one of the cockpit displays, one of the LCD panels off of an A320. And this display right now is telling the pilots that the pressure inside of the ducting is through 36 psi and the temperature is 190 degrees Celsius. I'm going to guess that this is probably with one engine running and it's at idle. Also, you're probably going to have a over temperature indicating system for the ducting. That's a significant issue for transport category jets, big business jets, big turboprops, and large turbine-powered helicopters, because this ducting is really thin, so it'll be light, but especially where the duct pieces come together, you got to have a clamp that goes around it, that goes all the way around it. And if this clamp becomes loose, then you may have hot air leaking out. And like I said, we're talking 200 to 300 degrees Celsius. So what if there's a wire bundle running across here? It could actually melt the insulation and wires could start touching anything. Or there might be some rubber or Teflon component right here in the airplane and it could melt it. And I really don't like it when my airplane melts. So it's common, well actually you're going to find some type of a temperature indicating system, temperature warning system for the pilot. Again, this is out of an Airbus A320, and there are several different loops, fire detection loops. The APU's in the back of the airplane, and alongside the duct is a fire detecting loop. And the right wing duct, of course, they're probably going to use that to heat the leading edge of the airfoil, as well as allow the main engine to pump air into it. That's going to be a loop. There's a loop here next on the right, and then there's a separate loop for next to the engine and for the duct for the pylon. So if we've got the main engine here and the pylon's coming up to the wing, there's a separate fire detecting loop just for the pylon, because there's lots of fuel and hydraulic system lines coming in here, and you probably don't want to heat those things up. So on this airplane, it looks like there's one loop for right engine, one loop. There's two loops, 3 for their left wing, 4 for the right wing, and 5 for the APU, because if I'm reading this correctly, this loop right here is included in the right wing. So there's actually 5 fire detection places where it could tell the pilot that you're getting hot air leaking out of the duct somewhere. So let's say, for instance, number 5 went. So it's telling you that somewhere along this duct there's a leak. So what you're going to do is, if you're getting power off the APU, you're going to shut the APU and you're going to close a valve so that no air from the rest of the system, from the engines, none of that hot air can feed that duct and melt anything. Of course, if you take bleed air off of the engine for any reason, it's going to increase fuel flow if you maintained the same power setting, the same thrust. Because if you take some bleeder off of the engine, the thrust will go down. And if it's not a computer-controlled engine, you'll have to push the throttle forward a little bit. So if you turn on the engine anti-ice, fuel flow is going to go up if it's a computerized engine, because it's going to try to maintain the same thrust. Or if you turn on the engine anti-ice and you want the same thrust, you're going to have to push the power lever forward a little bit to keep the same thrust going. And of course, we're probably going to run the pressurization system, and we might be running airframe anti-ice. So typically, this is going to increase fuel flow, even though you're still developing the same amount of thrust, because you're taking energy off of the airplane. And of course, if you turned it on and didn't change the power setting, or if it's a non-computer controlled engine, and you just turned on one of the bleed air systems, like you turn on the engine anti-ice, for instance, the thrust is going to be less. Fuel flow might stay about the same. So you'd have to push the throttle up if you wanted to get the same power. So there's going to be negative effects on fuel flow and on power developed. This is the section on thrust augmentation and engine construction. First, thrust augmentation. There's 2 basic ways to significantly augment or add to the thrust of a jet engine. One of them is water injection, one of them is afterburner. First one we're going to look at is water injection. Of course, if it's a hot day or a high altitude day, then the number of molecules per cubic inch available to go into the engine, if the volume is the same, there's less molecules going to get in the engine, so the thrust is going to go down. So we're going to try to mitigate those issues and actually increase the amount of thrust. Net thrust is the weight of the air over acceleration due to gravity, and the weight of the air is the second velocity of the exhaust minus the velocity in the intake, plus weight of the fuel over acceleration due to gravity times V2, because V1 is going to be 0, plus, that's area of the jet times pressure in the jet minus pressure ambient. But what we're going to do is we're going to add weight of the water, and it's going to be squirted in just like the fuel is. So its exiting velocity is going to be V2 and entry velocity is going to be 0. So we're going to add to the net thrust by adding water. That's one of the ways that we're going to increase the thrust. Since we're adding more mass, that makes up for the fact that there's less air going into the engine, less mass can be accelerated, less air can be burned. There's less air to burn and less air to cool. And the other way that we can increase the thrust is by cooling down the air hitting the turbine inlet guide vanes. Essentially, if we squirt water into the engine, then it's going to, as it evaporates, the water will take energy out of the air that's going through the engine and cool that air down. Well, if we have colder air, we can burn more fuel and still not hit redline EGT. So during water injection, we increase the mass of gases that are accelerated by the engine by adding water, and we're lowering the temperature so we can burn more fuel. If we burn more fuel, then exhaust velocities will be higher and the pressure in the jet will be higher, and both of these will add to engine thrust. There's a couple of different places you can put engine water into the engine, or you might even do it in both. Here's a JT9D. That was put in the Boeing 747-100. It went into service back in 1969, and some of those engines had water injection. Now, I'm familiar with water injection in J57s that were put in B-52G models. We call them steam jets, and water was squirted into the compressor section, and water was also squirted into the combustion chamber. As that water vapor is going through the compressor, the water is going to turn into vapor, and it's going to pull energy out of the air that it's in, so the temperature of the air is going to go down. That tends to contract the air, so we tend to get more molecules per cubic inch. That'll help our thrust. And if we also squirt water into the combustion section, then by the time that all the air hits the first turbine inlet guide vane, as that water evaporates, it reduces the temperature a little bit, so we can squirt in more fuel, yay, and burn more fuel, and of course more fuel means we can get more thrust, and we can burn that more fuel without exceeding redline EGT hitting the turbines. So if you really want to get use out of this water injection system, squirt the air in front of the squirt going into the compressor, and squirt the air in going into the combustion chamber. If you do it right, you can get a 30% increase in thrust, which is quite a bit of thrust. If you're used to an engine with 10,000 pounds of thrust, you can now get 13,000 pounds of thrust. So that is a big change. And of course, you're going to do this on hot and high altitude, high pressure altitude days. Of course, if it's really, really cold, the water in the tanks in the airplane might freeze. But hey, if it's cold, the engines are going to be able to produce enough power so you don't need water injection on cold days. So you don't have to worry about the water freezing. You don't put water in the tanks. One of the disadvantages to the injection system is that it doesn't last forever. On B-52s, it lasted at about 2 minutes. There was enough water to last for about 2 minutes. If you do have an engine that has water injection, you're typically going to have a dry thrust rating, which is typically redline power, and a wet thrust rating, which is higher than that, and they would both be listed in the type certificate data sheet. Water injection, some old transport category airplanes, and some old military. I don't think there's any engines being made today that use water injection, but you might fly a 707 if you go to fly in a third world country to get your airline career off to start. And there's definitely Boeing 747-100s out there still flying. Of course, the second way to increase thrust is by use of afterburners. Afterburners are reasonably simple. If you take a jet engine, you can do it on a turbojet or a turbofan, and of course you've got the fuel burning and accelerating the gases, and 70% of the air is used for cooling. So guess what's left over here? 70% of the oxygen. So if we put in some fuel nozzles and we put in an injection system or an ignition system, and we're going to have to run it continuously, and we're also going to put in some flame holders. I'll talk about that later because the flame tends to get burned out. Then we can have some more flames going on in here, and of course the velocity will go up and the static pressure will go up, and of course both of these are going to give us an increase in net thrust. I like afterburners. In Great Britain, they call it reheat. Who uses it? The only civilian airplane I've ever seen use it was the Concorde. The vast majority is military fighters. Of course, the B-1 is not a fighter, but it has afterburners on it. Yep, got that one already. Oh, wait. And if it's a low bypass turbofan, then in addition to, we'll say it's a military jet, there's going to be a low bypass. They might have more than one fan for the bypass fan. So not only is 70% of the core air available, guess what? You've also got the bypass air available. So now you have lots of air, or lots of oxygen that you can burn. And of course, you get more thrust by adding fuel, igniting it. Static pressure in the tailpipe goes up, velocity goes up as well. And you can get a pretty good kick. 50% increase in thrust is pretty typical. The downside is your TSFC climbs up like crazy, 200 to 300. So if you're cruising along in a military turbofan and a jet fighter, say an F-16, and your TSFC is 0.5 and it goes up 300%, it's going to go up to 1.5 during use of afterburner. So you're going to run out of gas 3 times faster. So you don't want to use your afterburner all the time. Now, if you're in a fighter jet, you're going to typically use afterburner for takeoff, initial climb. If somebody's trying to shoot you down, you're probably going to use the afterburner. And a fourth one would be to shoot the bad guys down. If you want to catch up to them, you may have to use the afterburner. So we're going to say that there's 4 uses, typical uses for afterburner. And it's manually controlled. On an F-104 or on some old style military jets, the throttle grip is on the right hand side, and of course you're going to put your fingers around it, and you're going to push it all the way up to right here, and that would be military power, which in FAA parlance would be red line or takeoff power or rated power. And if you slid that throttle over and then pushed it up, this would be the afterburner. And on some engines, the farther you push it up, the more fuel gets squirted into the afterburner. So you actually have different amounts of afterburner. And that's pretty common on newer fighter jets. The farther you push it up, the more afterburner you get. Of course, supersonic engines have convergent-divergent nozzles. So here's the last turbine blades. Here's the compressors out front. And of course, in here we're going to have, from here forward, we're going to have this the afterburner, and we're going to have our fuel nozzles and our flame holders and our ignition system, which we're going to run continuously. Whoops, what did I do back here? Oop. So of course in here it'll be less than Mach 1. Right here where the shock wave is, it'll be right at Mach 1. And inside the divergent portion, it'll be greater than Mach 1.0. But you've seen this all before. Now, what you haven't noticed is that on military aircraft with afterburners, this nozzle changes shape essentially, and I'm oversimplifying it. If this nozzle hinged right here, let's get rid of all this mess. If this nozzle hinged right here and right here, this would go out and could come back in and could come back in. Okay, if you're at idle speed, all you want to do is let the engine run. So at idle speed, the nozzle is going to be wide open, and you're not worried about how much thrust you get. Now, next, at cruise, all the way up through military power, we don't really worry too much about the convergent nozzle because we're cruising along at, say, Mach 0.8. And so we can have gases coming out of here at, say, Mach 0.6 because the gases are really hot. So we only need this to be crunched in enough to get an optimum airflow. So actually, this nozzle is going to be constricted just enough to get us a decent velocity coming out during cruise. That being said, when we go into afterburner, we might want to be going supersonic, and we want this to be like Mach 2 or Mach 3 or something. And so in order to do that, we could just turn on the afterburner system, and of course the velocity and the pressure would go up. But we're adding so much energy that if we left it constricted, just like we did for cruise or military power, then we'd have a backup of pressure and wouldn't get a highest velocity. So actually what's occurring is during Mach speeds, it's actually at its widest at Mach. And even though it's bigger than it was at cruise at military power, we're still going to get that shock wave to occur at Mach 1. So if you watch Top Gun at the beginning of the movie, at idle, the nozzle's wide open. As the pilot runs the throttle up towards military power, the nozzle gets a little bit smaller, and then as they go into afterburner, the nozzle widens out again. Afterburner components, there's just 4 of them. I already drew them. Flame holders are kind of hard to describe, so here's a picture of a flame holder. These flame holders inside of the engine, if we cut the engine from the side, if there was the engine, and the fuel nozzles are right in front of it. If we had these fuel nozzles burning and we didn't have these metal rings going all the way around, the flame would tend to get blown out. So we need to cause some turbulence so the flame will slow down a little bit and control the burn. So you're always going to see flame holders when you look up the tailpipe of a supersonic engine. In addition to, of course, the exhaust pipe, the fuel nozzles. And there's going to be a separate ignition system from the main engine system that's used during engine start. And this one is going to be run continuously because it's kind of hard to keep that flame burning. So they're going to run the ignition system continuously. Engine construction. If you design your engine so the turbine section can allow higher combustion exit temperatures, that is the temperature of the air that's actually hitting the first turbine inlet guide vane, then that's going to reduce TSFC. The question here is, why does the TSFC go down? Well, if we've got our engine, a couple of turbine blades, all those compressors out there. Man, I think I'm just getting lousier at drawing jet engines. And let's say that the typical air hitting it before was 1,000 degrees Celsius, and the turbine blades can handle that. But if we made the turbine blades out of a metal that could withstand higher temperatures, say 1,500 degrees Celsius, then that means that that cooling air that's coming through the engine, not only do we need air to burn, but we need air to cool and mix with the air that's getting burned up, so that by the time the air hits the turbine section, it's cooled down a little bit. If we can withstand higher temperatures, then that means we don't need as much cooling air. Well, if we don't need as much cooling air, then that means that we can get away with a smaller compressor. We don't need as big of a compressor anymore. Well, we're still going to burn the same amount of air, but now we don't need as much cooling air, so we can use a smaller compressor. If the compressor is smaller, then either we don't have to extract as much energy and we can get more thrust out the tailpipe, or, since we don't make turbojets anymore, that turbofan, now more of the energy that's going to the turbines, it's the same energy going to the turbines, but now less of it has to stay here in the compressor and more of it can go to our fan. And of course, if we have a turboprop with a gearbox, more energy can go to the propeller. Or if we have a turbo shaft engine, more energy can go to the output shaft. So if less of the fuel energy is used, is probably a better way to describe it, to drive the compressor, so a greater percentage of the fuel energy is used to develop thrust or power an output shaft or power a propeller. So guess what jet engine manufacturers tend to do? They tend to make turbine blades that can withstand higher and higher temperatures. Coefficient of expansion, that means if you have a shaft and you've got a turbine blade or a compressor blade on it, and when it gets hot, it's going to expand. So you better make sure that you have enough room on that engine case for it to expand to. Different metals expand differently. Thermal conductivity, how easy it is for heat to get to this blade, and if we're blowing bleed air through it, can this heat leave the metal very well? We'd like it to leave the metal very, very easily. And of course, during engine start, it's cold, and we're going to run, if we got another turbine blade here, we're going to burn that fuel, and it's going to start heating up that blade, and we're going to go from, say, 15 degrees Celsius all the way up to 1,000 degrees Celsius, in 5 or 10 seconds. So we need to be able to make this out of metal that can stand it getting heated up very, very rapidly, yet still maintain its strength. So you're going to be spending some money on this metal in the turbine section. You don't have to memorize any of these numbers, but what I find interesting is that if you multiply all of these numbers by about 2, you'll find that that's about where they melt. For instance, aluminum alloys melt at around 1100 degrees Fahrenheit, but they lose their strength at around 650 degrees. Iron, for instance, melts at around 2800 degrees Fahrenheit, and 1250 is about half of that. 1250 is where iron alloys start losing their strength. So you can see here that these are in order of metals that can withstand higher and higher temperatures without being damaged and being able to maintain their strength. And these are typical alloys that engines are made of, although aluminum doesn't get used inside the engine much anymore because we're going to run high temperatures. Okay, I'm not going to ask you to draw this graph on the test, but you'll see how fast aluminum goes down. That's the worst case scenario. Titanium goes pretty strong, then whoosh, and check out nickel alloy. It can stand the highest temperature and still be significantly stronger than nickel, or significantly stronger than steel, and significantly stronger than titanium at a really, really high temperature. So you're going to see nickel and cobalt alloys in turbine sections of jet engines. Of course, they cost a lot more, but hey, it's worth it. The turbine section is more stressed than any other part of the engine because it has to withstand the highest heat. It has to withstand the highest velocities, trying to blow the blade down. If we've got a shaft and we've got turbine blades inside of the engine, this air velocity is literally trying to push the blade back down. Centrifugal force, of course, is pulling the blades outward. And although the engines don't vibrate very much compared to reciprocating, they do vibrate some. So the turbine section has to withstand all of these stresses. The turbine blades do, especially the rotating turbine blades, have to withstand all of these stresses. One might argue that the second most stress section is the compressor blade because it has to survive vibration, centrifugal force. It's got velocity pushing on it, although it doesn't have nearly as much heat. You might think maybe it's the combustion chamber, but the combustion chamber doesn't have any moving parts, so it doesn't have to put up the centrifugal force, and it doesn't have any air blowing trying to bend it down. So I'm going to say that the compressor is the second most stressed section, even though it doesn't get very hot in there. Now, there are some new materials on top of cobalt alloys, nickel alloys. They have been looking at coating the turbine blades with ceramics for insulation, essentially like the tiles, the heat tiles on the space shuttle. The problem is that if the ceramic coating doesn't expand and contract, at the same rate, that is, it doesn't have the same thermal expansion characteristics of the metal inside of it, it doesn't work out so well. There are some parts on engines that they've been looking at making out of ceramics, like the engine case on the inside could be made out of ceramics. And in particular, the fan blades on modern turbofans. If you look at the GE90, the Trent series engines from Rolls-Royce, the Pratt & Whitney 4000 series engines, they're making the fan blades out of composites, and composites are essentially fibers glued together, but they're very lightweight and they're very strong, and you can make them into interesting shapes and still be very, very strong. Of course, there are a few non-structural materials that are found on the jet engine. Teflon, nylon, rubber, and a lot of different plastics are on the engine for seals. Of course, these are not going to be anywhere where the temperature is too high, although Teflon can handle a pretty high temperature. If you have any questions about engine construction, please contact me. If you have any suggestions about how to make this lecture better, please give me a call or an email or something. Thank you.